This is a collaboration between the computer scientists at the University of Maryland, College Park, and the surgeons at R. Adams Cawley Shock Trauma Center, University of Maryland Medical Center. In this project, we developed an augmented reality surgical tracking and visualization system that can assist surgeons in catheterization. Conventionally, catheterization in surgeries relies heavily on surgeon's experience as the catheter becomes hard to locate when it has entered the patient's body. Due to its thinness, it is difficult for depth sensors such as Kinect to detect the catheter. Our system consists of three components: a sensing unit, a processing unit, and a display unit. We use an off-the-shelf Logitech C920 web camera, a laptop computer for processing, and a Microsoft HoloLens head-mounted display. There are three color bands attached to the catheter that will be used for tracking. This modification makes minimum change to the catheter's shape, weight, and functionality. We can calculate the 5 degree of freedom information of the catheter from the color band's image. Given the coordinates of the color band endpoints in the image and the length of the color bands, our problem can be seen as a special case of the perspective 3-point problem. We calculate the angle alpha formed with the catheter and its image on the image plane and use it to determine which solution to the P3P problem to use. Locating the catheter requires the positions of the color bands in the image. Our image processing starts with undistorting the image and using predetermined color thresholds to find the pixels belonging to each color band. The catheter axis is calculated by fitting the pixels into a line. We then calculate the gradient along the axis, getting strong responses at the endpoints of each color band. After smoothing and thresholding, we find the endpoints as the weighted centers of the kinetic components of the gradient image. The position of the catheter is calculated for each frame. Our system is easy to use. First, the user uses hand gestures to move the virtual catheter in the AR application to overlay the real catheter. Then, a voice command triggers the system to find the transformation from the camera space to the HoloLens's coordinate system. After this, the catheter is tracked in the subsequent frames. We took the system to be tested by neurosurgeons in a realistic experimental environment. An external ventricular drainage procedure is performed using our system on a cadaveric head. We test the stability of the tracking algorithm by tracking a static catheter. Noise in the image causes the detected catheter to jitter. The root mean square of the change in the calculated tip is 0.33 mm. We then test our algorithm's accuracy by pointing the catheter tip at points over a 2D grid. We're able to achieve a 0.58 mm average accuracy in this case. We also test the accuracy on a 3D printed structure with 3 faces sublime whole grids. The accuracy on faces A, B, and C are 0.49, 0.93, and 1.12 mm respectively. We observe a latency of 95 milliseconds in our system. Our analysis shows that it takes our algorithm 22.6 milliseconds to process a frame, with nearly 80% of the time spent on rectifying the image and calculating the gradient along the catheter axis. Parallel implementation using GPU and cameras with low image capture time can greatly reduce latency. To summarize, we developed a low-latency, high-precision 5 degree of freedom catheter tracking method. And with AR, we can visualize the catheter inside the patient's body, assisting surgeons in catheter placement. Thank you for watching this video.